Hey guys, welcome back to AP Chemistry Unit 3. Today we're going to be talking about the kinetic molecular theory with chapter 3.5. So the enduring understanding for this chapter is gas properties are explained macroscopically, using the relationships among pressure, volume, temperature, moles, gas constant, and molecularly by the motion of the gas. So what does the kinetic molecular theory entail? So the kinetic molecular theory, sometimes abbreviated KMT, relates the macroscopic properties of gases to the motions of the particles in the gas. The Maxwell-Boltzmann distribution describes the distribution of the kinetic energies of particles at a given temperature. And so there are 5 postulates to explain why gases have certain behaviors and properties. And this is adapted from Sean Bryan at the College Board. And he explains these 5 postulates in his video. And so the first postulate is that gases are composed of molecules that are in continuous motion, traveling in straight lines and changing direction only when they collide with other molecules or with the walls of a container. And then the second postulate is that the pressure exerted by a gas in a container results from collisions between the gas molecules and container walls. And the third postulate is the average kinetic energy of the gas molecules is proportional to the Kelvin temperature of the gas. So if you know from AP Physics or another class, that kinetic energy is really just like the active energy of the molecules, and I'll get more into what that means later. And then so these last 2 postulates, 4 and 5, are marked in red because these are like in chemistry, like they're in chemistry theory, like they don't actually apply to real gases, and that's what we're going to get into chapter 3.6 and why these 2 postulates don't apply. But we're gonna explain them for the kinetic molecular theory's purpose. So the fourth one is the molecules composing the gas are negligibly small compared to the distances between them. And then the fifth one is gas molecules exert no attractive or repulsive forces on each other or the container walls. Therefore, their collisions are elastic. And then in parentheses, do not involve a loss of energy. So that's just what it means for them to be elastic. And so we're going to go back to these like laws, and we're going to explain them using the kinetic molecular theory. And so here's Boyle's law again. As the volume increases, pressure decreases, and as the volume decreases, pressure increases. And the kinetic molecular theory explanation is that, when the volume of a container decreases, the particles collide with the sides more often. More collisions increase the pressure in the container. So that just goes back to this first postulate, colliding with the walls of the container. And then Charles' law, there's this direct relationship between temperature and volume. And the kinetic molecular theory explanation for this is that when the temperature increases, particles move faster, causing more and stronger collisions with the sides of the container. Volume increases to keep the pressure constant. So we go back to this, the average kinetic energy of the gas molecules is proportional to the Kelvin temperature. See, when the temperature increases, particles move faster, and this faster is relating to the kinetic energy of the molecules. And then it also relates with that collisions with the sides of the container. And then the volume just increases to keep the pressure constant. And then we have Avogadro's law, which is that direct relationship between moles and volume. And the kinetic molecular theory explanation for this is that adding more molecules, more particles to a container causes more collisions with the sides of the container. The volume increases to keep the pressure constant. And then we have our last law, Gay-Lussac's law, which is explaining this direct relationship between temperature and pressure. And so the kinetic molecular theory explanation for this is when temperature increases, particles move faster, causing more and stronger collisions with the sides of the container. And then this is the chain, like the part that's different. The pressure increases because when the volume is constant. So because the volume is constant, the pressure is able to increase. And so how do you determine how much energy these particles have when they're moving? So I keep on talking about this average kinetic energy. And so you can use these particles' velocity in their random constant motion to determine their average kinetic energy. And you can use this equation. So Ke, which is that average kinetic energy, is equal to 1/2 mv squared. And so m is the mass and v is the velocity. And you're not really going to be using this equation all that much, but you want to understand the relationship between velocity and average kinetic energy. So as the velocity, or the particle's direction and speed, as they increase, the kinetic energy also increases. And then we move on to the average kinetic energy of particles is directly proportional to the temperature of the substance in Kelvin. So as the Kelvin temperature increases, the kinetic energy increases also, which we explained earlier. And so I'm going back to chapter 3.3 to kind of relate these topics together. And so then we talked about the vapor pressure, which is the pressure exerted by a gas in equilibrium with its liquid phase at a given temperature. And so we said as the temperature of a liquid increases, the vapor pressure increases. This is because more molecules have enough kinetic energy to release from the liquid and become gases. So as you have more gases, your vapor pressure is going to increase, because you have more gases. And this is how that relates. Because there's more, the temperature is higher, these particles have more kinetic energy and then can become gases. And so as the temperature, this is this Maxwell-Boltzmann distribution. And as the temperature increases, more molecules move at higher speeds, and the average speed of the molecules increases. So as you can see, this is at 100 Kelvin, 300 Kelvin, 600 Kelvin, and 1,000 Kelvin. And the x-axis is the molecular speeds, how fast they're moving, how fast the particles are moving. And then these are the number of particles. And so under all of these curves is the same number of particles. But what's different is that the 1,000 Kelvin spans all the way past 2,000, way past 2,000. But 100 Kelvin only gets to 1,000. And so there's going to be more, and then there's going to be a line, let's say around here maybe. And so as you have, there's going to be a line right here, and this line represents everything past this line represents particles that have enough kinetic energy to become gases. And so as you increase the temperature, there's going to be more particles under this curve, which will have more kinetic energy and then will become gases. And that explains why as the temperature of a liquid increases, the vapor pressure increases. This is because more molecules have enough kinetic energy. So these will have more kinetic energy. See, moving way 2,000 compared to 1,000 is a huge difference. And so if you found this lesson particularly confusing or you just wanted to review, I strongly recommend you watch Sean Byron's video from the College Board. I have it set up so it takes you directly to 3.5. It's a really good video, and I'm so thankful that the College Board is able to provide us with this great content. And he's a really, really, really great teacher also. So if you ever need any review, or you thought my lesson was particularly confusing, or you just didn't understand something, I encourage you to watch the videos. And so here's today's bibliography of my sources that I used. And that's about it. So I'll see you guys next time for 3.6.